Okay, so continuing with what we were talking about, we gave two examples of real valued functions. And the second one was this example of trying to figure out what price would you sell a bunch of items based on what you have observed in the past. So this is actually a mechanism design question. Sorry, 1 second. And you can think about mechanism design itself as an offline learning problem. It's because mechanism design requires knowing distributional assumptions about agents types. When does this happen? Think about the simple example of a single item second price auction with reserve prices that Chara mentioned in the previous session. In this case, bidder valuations are coming from this distribution D that could be supported with between 0 and 1. And you can think of the CDF of this distribution being function f. Then the optimal reserve, or if you want to just think about the revenue that each reserve function can get you, is the value of the reserve times the amount of the fraction of people who are willing to pay that reserve, which is 1 minus the CDF of R. So to know what is the revenue maximizing auction, we actually need to know the CDF of the distribution. This is where a distributional assumption or need to know the distribution of agents naturally enters mechanism design. But it goes way beyond this as well. You can think about the goal of learning in mechanism design to find optimal mechanisms when this distribution D is unknown. So that is, given a large class of mechanisms, M, for example, all possible reserves for single item, second price auction, and a utility function U, which could be revenue. The set of agents types that are sampled from an unknown distribution D is going to help us find the mechanism that approximately maximizes the utility that we are hoping to get. So this is a way of thinking about mechanism design as a learning problem. Now, I talked about offline learning, and this is a very common paradigm in machine learning where the data is coming from a distribution. But both in mechanism design and even in classification, there are cases where there is no distribution. It might be that the environment is evolving over time in unpredictable ways, and we don't want to make any assumptions about how it's evolving. Or it could be that the decisions we are making right now are going to actually impact how the future instances are going to be generated. So we want to make these decisions as soon as we receive a new instance, and we cannot wait until the end of time. But at the same time, we have no distributional assumption. So how can we learn? What are some examples of this setting? Going back to the two examples of real valued functions, for example, if you're driving from home to work, traffic fluctuates because of the construction that might be happening, potholes, holidays, the traffic patterns change, and it's not predictable necessarily, and it's not coming from a distribution. Also, in terms of what price would you set for your items, willingness to pay also fluctuates around holidays, pandemics, and many other things that unexpectedly and unpredictably happens in life. So we need this kind of a robustness to changes, which offline learnability does not provide. This is where online learning models come in. So to model this in online learning, we say that we're trying to learn using still classifiers from some fixed set of functions, H, on a sequence of instances that are arriving. At round T, we are picking a classifier HT, potentially from a distribution over this set of hypothesis H. Then an instance XTYT is picked by the nature. Now, nature is not necessarily random. It could be potentially adversarial or malicious. The algorithm sees this instance XTYT and will incur a loss. This loss for us is that misclassification loss, which is the indicator variable that shows that we made a mistake. Now, what we want to minimize in an online learning is very similar to trying to minimize our error compared to the best classifier. The difference is that the best classifier itself is being defined in hindsight. What do I mean? We call average regret the difference between the average loss that we are incurring and the loss of the best classifier H that I could have used had I known the sequence ahead of time. And this is going to be less than some epsilon. The typical values of epsilon you want to think about are within range of ln of H over T. So this would be if you can get this amount of epsilon, the guarantees you're getting are almost matching actually your offline learning guarantees. So this is an online learning framework, and I gave you an example of it in classification, but it can be also used in mechanism design or for real valued functions. Thinking about it as a mechanism design question, on round T, you're trying to pick a mechanism MT, and this again could be picked randomly. Now, new agent types are going to arrive. This is a vector of VT and could be coming by nature, but potentially adversarial as well. The algorithm can see this type and get utility U of MT-VT. Again, analogously, we are going to define average regret here now a maximization problem as the difference between the utility of the best mechanism over this set of types that we have versus the utility that our mechanisms that we picked at time T managed to get. And again, this is going to be epsilon of the same order that we discussed before. So you can think about this as online learning can also be applied to mechanism design. And just today, in the later part of this session, I'm going to give you more information about how we can do this. But how can we actually get these online guarantees? Our first attempt would be to let's repeat what worked in the offline setting. So what worked in the offline setting happened to be doing this empirical risk minimization. Just pick the hypothesis or the classifier that performed well historically. So what happens if we do that now? If we just repeatedly do empirical risk minimization, how bad can this be? So let me now formally say that here, HT is being repeated empirical risk minimization means that at time T, I look at the history so far and try to minimize that function, loss function. This is actually not a very good idea. And the reason it's not a good idea is not because it's about empirical risk minimization, it's because it's a deterministic algorithm. And if you think about this, if nature is going to be actually a malicious adversary, who knows what you're doing, this malicious adversary can pre-compute any deterministic function. It can, based on the history that it has generated and knows what you're doing, it will know what kind of function you're going to be using in the next round. And because it can pre-compute that, it can use an instance, EC'20, that happens to be pretty terrible for exactly the choice that you made. So in general, deterministic algorithms don't work well in online settings because of this adversarial nature. But to be honest, this is not that terrible of an algorithm in the sense that it's intuitively doing what it should be doing. While it's deterministic and it has problems, the idea of using functions that historically performed well is a good one. And we can think about how we can introduce randomness while still trying to pick functions that perform well historically. One algorithm that does this is called follow the perturbed leader. And what it's doing is that it basically takes empirical risk minimization, except rather than looking at just the empirical risk, it's going to add some eta h, which is some noise coming from some fixed distribution. In a way, it's perturbing the historical performance of different options that was available to it, and then it picks the best perturbed one. Without going into much detail, let me just tell you what kind of regret you can hope to achieve from this follow the perturbed leader algorithm. And it's known that the average regret in this setting is going to be that square root of ln of h over t. This is exactly what I said is what, if we can get, we're almost getting bounds that are similar to what we were getting through uniform convergence even in the offline setting. So this is actually a really great algorithm for online optimization, and it's one of the most popular ones. There are other algorithms that are really useful to know. another very good approach is called, well, it's also trying to sort of balance randomness while still rewarding good historical performance. And the way it's doing it is that it thinks of maintaining a probability distribution over all the options that you have. So all the possible classifiers in H, you can start at being uniformly at random. Then at time t, you decrease the probability of functions that performed poorly on that time step. So going into the future, you keep downgrading anybody who did not perform well. It's still random, but somebody who didn't perform well has a much lower probability of being picked in future. What does this look like? So you can think about this as multiplicatively reducing the weight of different options. This is called the multiplicative weight update algorithm, or also known as hedge, where you initialize weights to all be 1, so you're equally weighing all possible options. And then at time t, you pick a function from your class proportional to these weights. So in a way, you use a scaled version of these weights to tell you the probability that you should be picking ht. Now that you do this, you receive the next instance, xt'20, and incur the penalty that you were going to incur, which was the loss of what you played over this instance. What you're going to do is, before the next step, you're going to update these weights. In a way, the weight for the next time around of any function is going to be multiplied by 1 minus epsilon if that function made a mistake. Especially thinking about this loss as being a 0, 1. This is basically smaller than 1, so you're reducing the weight if a mistake had happened in the previous time. And you're leaving it as is if no mistake had happened. So this is a multiplicative weight update for loss minimization. And it also gets very similar type of guarantee as our follow the perturbed leader algorithm. That is, if you set this epsilon properly, you can get the average regret that is, again, logarithmic in H and is 1 over square root of t. So I wanted to just tell you a little bit about why this algorithm works, because it does help to understand why this kind of randomly taking decisions but still downgrading bad options is useful. And in a way, you can think about this as these weights that we've assigned to hypotheses, to these classifiers, are a measure of credibility scores that we have added to these functions. Now, let the total amount of credibility that exists in our set of options at a time t to be wt. So this is a sum of their total weights. If there's a high probability that we make a mistake at one round, there will be a huge drop in this wt. Why? Think about qt as the fraction of the weight of functions in H that are making a mistake at time t. So qt is actually the probability that we make a mistake as well, because we are just picking randomly based on these weights. So in this case, the total weight at the last time step is just going to be a multiplication of the weight we start with, which is the number of options, being reduced at every time by how likely it is that we make a mistake. Now, if I take log of this weight, you can see that the prediction, the number of mistakes that I'm likely to make is actually entering this. That is, log of this total credibility is going to be at most the log of the credibility we start with minus the number of mistakes that our algorithm made times epsilon. So this is relating credibility with the number of mistakes that our algorithm is making. At the same time, credibility at any time step is lower bounded by the credibility of the best function, which is what we are trying to compete with. So let's say this best function h star is that function that is entering the regret. And the ln of my weight vector is always going to be at least log of 1 minus epsilon to the power of the number of mistakes that h star made, because that is going to be the weight of h star after t time steps. So putting this together, this upper and lower bound together shows that there is a relationship between number of mistakes that the algorithm is making and the number of mistakes that the best hypothesis is making. Now, I've been talking about number of mistakes because we talked about classification. But the same thing actually works for real valued functions, where the expected real value function that we are getting is going to be related to the quality of the best function that exists in our class. And this is how you get regret bounds. The two algorithms that I covered, follow the perturbed leader and also multiplicative weight update, both crucially use the fact that I know how each option would have performed, even if I never played that option. So how are they using this? In their update and in our optimization setting. For example, follow the perturbed leader for any age, even an age that it has never tried in the past, needs to know the total loss of that function age. Similarly, for multiplicative weight update, even if I don't play H ever, I still, to update its weight, I need to know the loss for it. So this is pretty reasonable in settings where this information is available, like classification. In classification, when I see EC'20, then no matter what hypothesis I had played, I can compute the loss of the other hypothesis, because that function is just something that I can compute by looking at whether another function would have made a mistake or not. But it's not so readily available in many other applications, and especially in mechanism design. Why not? So thinking about, again, the driving to work example, maybe you can see the traffic that you experience going from home to work, but I have no idea if another path that maybe Chara took would have been busy or not. So while I can see the loss or the behavior of the options I've tried out, the options that I've never tried out are much harder to know. Similarly, for revenue maximization, maybe I can see whether or not the item that I was listing at $10 was sold or not. But even if, let's say, Chara was willing and paid $10 for this ice cream, I don't quite know. Would Chara have paid $15? I don't know. And because of that, I don't have that amount of information to compute, what would have been the revenue had I increased the price slightly. So this is called partial information in online learning. And the most common version of this partial information is actually called Bandit feedback information, where the information you're getting is the loss of only that option that you tried out at time t. So at time t, I'm not observing the loss of everything. I'm only observing the loss of ht at that step. How do we deal with this lack of information? So one way to think about this is that previously, I kind of only collectively needed to know, for example, to even compute this, the total loss, I need to have a sense of whether this is high or low. But maybe it's not that important to know exactly what the loss is over t time steps. So intuitively speaking, if I have an unbiased and low variance estimator for a loss of each hypothesis that maybe I didn't even try, then that estimator can be used. How do we do this? Well, at every step, we can try out some, function uniformly at random with some probability. Because if there is some probability of trying it out, then I can use the loss that I received at that step to build an unbiased estimator for the loss of that function at that time step. Now, once I build these, unbiased low variance estimators, how do I use them? Well, I need to change my multiplicative weight update to incorporate these estimates so that now next time around when I pick a function, it takes into account this kind of random things I tried out and how well estimately they performed historically. These two steps are called exploration and exploitation. So exploration is when you just kind of randomly blindly try a bunch of things to see what works. And exploitation is that if you've tried something that, yes, it has been working, then you should be, again, try to exploit it and try it out more. In fact, you can think about a reduction that allows you to use any online algorithm, online full information algorithm, even in the bandit setting. how would we do that? There's an algorithm called exponential weights for exploration and exploitation. And at a high level, it's doing a reduction to a standard, like for example, multiplicative weight update algorithm. How can I think about this reduction? You know, my XP3 algorithm is at any time step only seeing my, only seeing the loss for that hypothesis at time t that was tried out. But it will create these additional losses before sending the value of all losses, all pretend losses, to multiplicative weight update. What are these pretend losses? Well, if I didn't try out something, the loss is going to be 0. If I did try it out, I'm going to just scale this loss so that it's going to be, you know, unbiased. It's going to be scaled by the probability, by the likelihood that I actually chose this LT of HT. I will talk about QT in a minute. Now, once I send this to the multiplicative weight update will send back to me a probability vector that I should be using to decide which one of these options I should be taking at what probability. That's shown in this probability vector PT. Now, QT, which was used here, is the probability vector that was given to me from multiplicative weight, almost that, plus some pure randomization. So basically, 1 minus gamma time, fraction of the time, I just go with what the multiplicative weight update suggested to me. The other gamma fraction of the time, I'm just doing some random, you know, sampling of all the different options that are available to me to sort of get a good sense of what they are. So this is a way to think about how we can go from, you know, having not enough information and using algorithms that assume a lot of information to still do online regret minimization. In fact, if you use this algorithm, you can show that essentially this algorithm is getting regret that is going to be now not logarithmically, but linearly in the number of hypotheses, but still 1 over square root of t. So this is what exponential weights for bandits achieves. Let me finish this brief overview of machine learning theory concepts by saying what we learned and what we didn't. We briefly talked about offline learning in terms of a setting where the samples that I have seen in the past are coming from a distribution, and I'm going to be tested on the exact same distribution again. What we didn't talk about here is what happens where our function classes are infinite hypothesis classes. And I will encourage you to read more about VC dimension or pseudo dimension if you're interested. We also talked about online learning. Online learning is a setting where at each time step, we have to choose a classifier at that time step that is going to be applied potentially to an adversarially selected instance XTYT. And we talked about 2 different observation modes. Maybe you can observe LT of HT, which was the bandit information. You only see the loss for what you tried out. Or in the full information case where you're seeing everything that matters. There are also other models that I didn't talk about, but we will touch on them briefly tomorrow. First one is that partial information is something that's more broad than just bandits. So for example, maybe what you're going to observe depends on what you did, but it's not just the one option that you did. So for example, if I am, you know, driving to work, maybe I see the traffic of every road that intersected the road I took, but I might not see the traffic on the roads that did not intersect mine. Similarly with auctions, you know, if I know that an item was sold at $10, I know that if I offered it for $9, it would have still been sold. So I still see the revenue that some of the other options are making, but I might not see the revenue for every option. So this is kind of a hybrid mode between full information and bandit. The other thing is that there's an entirely different way of thinking about learning where it's not that instances are just coming to you at random or you have no choice in deciding what instances to see, but you can in fact actively query these instances. These are called membership query learning, where you can actually create instance of your own, and you can ask the environment to tell you for this newly created example what would have been its correct label. So that's another model that we will briefly see tomorrow, because it's also very useful when you're especially thinking about Stackelberg games and optimizing them. So this is the end of the primer we had on machine learning theory. This is a good point to ask any questions about this, if there exists some.
Nika, we actually have an interesting question that came in the Q&A. Gary asks, this online setting focuses more on the Bandit side of the story than mechanism design so far. That was right when you completed the full information part. So my question is the underlying assumption about the player's type arriving across through iterations and revealed a valid assumption?
Is the assumption that we see them arriving one by one a valid assumption? Is that what you're saying?
I think that the assumption that they think is not valid is the fact that we get their type revealed.
So I said the type revealed because specifically what we're going to do next is a setting where the actual type gets revealed, but it could have been their claim type. So you cannot make that assumption, but there are settings that naturally bring that, and we'll see it. Excellent. So this is a good point to talk about what we are going to see next, which is almost the least amount of strategicness available in the agents, but still seeing how incentive compatibility can help with learning. So this is a setting where we're talking about revenue maximization in auctions, and sort of think about the offline version of this would have been what? Would have been, I have a class of functions, class of auctions M. I have a distribution D where the agent's valuations are coming from. And what I would have liked to do is, whether or not I know this V, I would have liked to maximize the revenue over this real valuations. Now, in the online setting, what this looks like is that at time t, I'm picking this auction MT, and the world is picking bidder valuations VT. What is important is that if the class of these mechanisms that I'm using are incentive compatible auctions, if the class of mechanisms are incentive compatible auctions, this basically means that the agents will reveal their true types, which is this bidder valuation VT. And if they do reveal their true types rather than some lie about their bid, I can actually compute their revenue for this, for all auctions. Okay, so what does that give me is that now I'm in a full information setting. Let me tell you that the title of this slide is saying something about myopic agents. Why are we talking about myopic, and what does that mean? It means that these are agents that either are unaware of the fact that we are learning about them, or they're agents that know that, or they're not just kind of repeating agents. They're not going to repeat again. Sorry, I don't know why my slides are moving without my control. So not quite sure what's happening, but maybe it's going to be okay. So what does this allow us to do? It allows us to basically think about this kind of gain matrix again, but a little bit more simply, that the auctioneer is picking a row at any time, MT, and the world is picking a valuation vector, VT, which we see it. And because we see it, we can know exactly what this whole game table would have looked like. That what is the revenue of MT, VT, basically. And again, in a regret minimization setting, what we are trying to do is that we are trying to maximize our revenue over T time steps compared to the revenue of the best auction applied to the same VT. This is important that it's the same VT, and because agents did not try to strategize beyond any single time step, and the auctions were incentive compatible in every time step, they actually provided us the VT that we now can really use to our benefit. So how does this compare to typical online learning? Once we've made this reduction, we are actually in a very similar setting to online learning. What is the setting? It's saying that we are working with just a learner who is picking one action xt at any time step, and the world is picking an action yt. We are seeing the action and we are seeing all the utilities xt, yt, and we are trying to basically maximize utility in the specific setting. And I can just apply the same regret bounds that I talked about just like 10 minutes ago and get a regret that is going to be square root of the number of, rows in this matrix over t, with a runtime that is going to now depend linearly on the number of rows. Why does it depend linearly? If you want to think about this, the multiplicative weight update was keeping a weight for every action that was available to the learner. So just to keep track of that or choose one based on these probability vectors, I need to spend a runtime that depends linearly with the number of rows that I have. And this is actually one of the challenges that comes in even in incentive compatible auctions. The fact that our auction classes are typically really large. We typically have multiple items, bundles, or bidder specific, discounts you might want to give, which makes this kind of polynomial runtime in the number of rows to be actually very prohibitively large for auctions. And that's something we want to avoid. And especially that in the offline setting, this is not a big issue in the sense that there are these, tools for computing optimal auctions that in some cases are actually known to be polynomial time algorithms, and in other settings are just heuristics that are known to perform well and run really fast. That can optimize revenue of an auction that is coming from a distribution. What we want to do is to tap into these existing, tools and compete with the best auction on changing valuations that we have in the online setting. This is called Oracle efficient online learning. Now, what is the power of Oracle? Why am I calling this Oracle? Sorry, the same thing is happening. My slides are moving for themselves. Sorry, 1 second. I'm trying to see what the issue here is because it seems to be running for itself without me telling it to. Okay, let's try this again. Okay, you see my slides? Okay. So what is this power of Oracle? The power of Oracle is that for any history, it can do optimization over that history. So it's basically that empirical risk minimization that we were talking about. If you have an Oracle, it's basically you can do offline learning. So what you're asking here is that for incentive compatible auction, is offline learning equivalent to online learning? And some things are known about these Oracle efficiency in online learning. In particular, if you have your functions that are linear in small dimensions, or what the adversary can do is just a few different options, not many of them, you can have online algorithms and run fast. But in general, these are not about auctions. There are examples where you can do ERM fast, but you cannot actually do online learning fast. What's nice is that what this work shows that is that incentive compatibility actually give us this kind of a structure that and full information and additional structure that allows us to actually do online optimization. And this structure is not just for auctions, but also many other combinatorial problems. Let me tell you that using this structure, you can get a range of results. For example, you can show that you can do revenue maximization in online auctions for VCG auctions, for NV free item pricing and level auctions. These are all incentive compatible auctions. Also, it can be applied to a wide range of other problems that are auction adjacent and mechanism design adjacent, but they're not themselves about revenue maximization. So what is the structure that is actually helpful here? The structure, what I've been calling D structure, is that there exists a set of D adversary strategies. These are bid profiles or valuations that sufficiently distinguish between any two learner strategies. What does that mean? It means that if I go back to that game matrix that I was talking about, there are D columns that if I remove every other columns, the rows are still remaining distinct from each other. And that is what it means to distinguish. What does it mean to sufficiently distinguish? It means that there is a tiny gap of delta between distinct utilities. So it's basically saying that you have discretized your auction class, which is a very standard thing to do. Now, if you have this, what are you getting as a result? We are showing that there is an Oracle efficient algorithm with regret that depends on the size of this D structure and square root of T, but also importantly that many auction classes have a structure that has a small size. And let me start with the second point, which is that let me give you examples of incentive compatible auctions that actually have this and talk about why that's the case. Let's start with, sorry, I think I still have that problem. Okay, let's try this again. Okay, let's start by this structure in second price auctions with individual reserves. So this is slightly different version of second price auctions where you're setting reserves for every type of bidder. So for students, there's a different type of reserve. For, you know, seniors, there's a different type of reserve. So the way to think about it is that you're setting a vector of reserve prices, and then what you're seeing is not one bidder, but a list of valuation of many bidders at a time, many types of bidders at a time. And if the way you run this is that any student, or sorry, any agent whose valuation is below the reserve, they just drop out. And if it's above the reserve, the highest remaining bidder wins, and they pay the maximum of the second price and the reserve that was set for them. So we basically need to say that there is a small set of bid profiles, not infinitely many of them, but a small set of them that will distinguish between all auctions in this class. How would I think about this? Basically, if two auctions reserve are different from each other, then the revenue on a bid profile where, you know, one bidder is bidding maximum and all the other bidders are completely uninterested in this item is going to be different. Because this is incentive compatible, by overbidding when nobody is interested in your item, you're going to just pay the reserve. And so if the two auctions differ on their reserve, they're going to actually differ on the value that they're getting here. And that's the value that's in the rows. So in a way, if I only look at bid profiles when one type of bidder wants the item so very much and everybody else is just completely uninterested, I have created a D structure. And this will give me a algorithm that has a regret that is linear in the number of bidder types and times 1/square root of T. And there is actually a slightly better structure I'm not going to talk about that achieves this with even a smaller structure. Now, in incentive compatible auctions more generally, in many of them, you can find these n bidder auction, you can find these D structures really easily. And it's because in these examples, there are a few parameters that define the outcome of the auction. In a sense, if I look at two auctions that are different from each other, and they're different because they differ on some valuation profile. Now, usually the winner and the revenue of these auctions are defined by only a few parameters, like who was the winner, who was the next in line, maybe who was the 10th in line. But at some point, there's going to be a point that we just don't care anymore who was in line. Now, if I take all of those and zero out everybody else, then the outcome of the auction does not change, because those reducing the bid of others that never entered the revenue maximization is not important. This will tell us that I only need to look at bid profiles where, for example, 4 non-zero bids have been submitted. And these are sparse bid profiles where fewer of them are available. So that's why, in general, incentive compatible auctions actually have this type of a structure that help. Now, how do you use this structure? To show that this structure can be useful, basically, we are taking an algorithm that is taking the actual history of the play plus some random fake history. And the random fake history that is generating is exactly those bit profiles that appeared in the column of this D structure. That is, I'm calling the oracle on the history plus some fake history. And this fake history is random in a way that I added some alpha I copies of the column yi to my optimization setting. This is oracle efficient, of course, because I'm calling an oracle on it, but is it no regret or not, which is what we need to understand better. And in fact, I can write this very similarly to what follow the perturb leader algorithm looked, which is that I'm trying to maximize historical utility plus a random perturbation. So this is very similar to follow the perturb leader. And in fact, you can use that similarity to say that if these perturbations were completely independent, that was what Kalai and Bampala, follow the perturb leader, was using, independent perturbations, then the regret is going to be small. But in this case, actually, our perturbations are the product of these rows for each x that row with the vector of all random variables that we have drawn, these alphas. So they're highly dependent on each other. They're not independent. But what's important is that there is still some independence that's going to help us. How does that work? We say that if we had independent perturbations, we would have actually had stability. What is stability? Stability means that our algorithm wouldn't keep switching between xt and xt plus 1 the next time around. And stability is actually a key property for showing no regret algorithms. Now, even though we don't have independent perturbations, the fact that any two rows in my D structure are different means that any two rows with respect to each other are a little bit random. And this with respect to each other a little bit random means that there's a small probability that I will switch from a specific row to another specific row. Now, I don't want to take each of these two specific rows to think about individually. There are many rows. If I do that, I can have union bound over very, very many rows that is going to kind of ruin this argument. Instead, I'm going to think about clustering bad events in this D structure based on what appears in this structure itself. At a very high level, basically stability is I can distribute it over different columns because every two rows are different from each other. If I switch my representation from xt to next day xt plus 1, one of these representation in one of these columns should have switched. Let's say it switched in column I. That means that I can actually think about how could it have switched. So if I look at these, what is appearing in this D structure, let's think about all these colored groups as groups of equal value. Then what I'm saying is that a bad event would have happened if either I pick a row that switches in the first column, or in the second column, or in a third column, or in the nth column. But because there are few groups now, the number of ways you can switch is just a few of them. So it's okay. The number of bad events I can take a union bound over is small. Now, each bad event is also not very likely to happen. That's a little bit harder to see. But at a very high level, there's a low probability of switching between two groups. Let's say that switching between two groups in column 1. What that means is that taking an action that one day belongs to the red group and the other day belongs to the blue group. If I look at the perturb utility of the action that I have picked, it's made up of the historical utility and the perturbations. Let's for a second forget about what I saw YT. If I forget about that, the historical part plus the other perturbations are more or less the same. It's not very significant what you observe in one day. In fact, the perturbations that are coming from column 1 are different from each other because there is a gap of at least some delta between these two groups, and that is being multiplied by alpha 1, which is the multiplier, the scalar for this column. Now, I would only switch between xt and xt plus 1 only if this insignificant YT is of the same order as this alpha 1 delta, so that seeing YT or not seeing YT would switch things for me. And this just does not happen with high probability because it's a very small range of random variable. So this is the high-level proof ideas of why auctions, incentive-compatible auctions, have structures that are useful and how we can use this structure. And importantly, what we're seeing is that in many incentive-compatible auctions, computing online optimal auctions on changing preferences comes for free. In a way that we don't need to have new optimization tools, we can just use the empirical risk minimization, but differently. Before I finish, let me highlight a couple important things about this incentive compatibility and myopia. We work with incentive-compatible auctions in the sense that in every round of the auction, the agent revealed its actual valuation VT, and that really helped us know exactly what we are going to get all throughout for all the other auctions. This gave us this full information plus the structural properties that I discussed. But myopicness was also important. The fact that these agents were myopic meant that agents didn't know or care that we were learning from them. If they did, a smart agent would still have incentive to lie, to, for example, underbid and not reveal its actual valuation in a hope that the future mechanisms in future time is going to be more forgiving. So it's not sufficient to have incentive compatibility per round, but you also need to have myopia if you want to apply these tools. What we are going to see tomorrow, and we are going to actually see a range of more strategic interactions where we really have to balance incentive compatibility and this kind of the fact that agents might not be myopic. And we will get down to discussing how we can do that a lot more in tomorrow.